Okay, hi everyone. So now I will continue on the third chapter for our syllabus, which is the principles and application of atomic absorption spectroscopy. All right, so before this, during the first instrument that you have learned is UV visible spectroscopy. So as I mentioned in the previous lecture, UV visible spectroscopy is usually used for molecular compounds. So before this, we have looked at into the application of UV visible in detecting paracetamol, in detecting catechin, which is a food coloring. So all of these are molecular compounds where it can produce a good absorption spectra for UV visible. So now we are going to look at atomic absorption spectroscopy. So now you need to imagine yourself, imagine that the molecule that or whatever that we have from your analytes need to be atomized first before you do your analysis. Okay, so absorption and emission of light by compounds is generally associated with transition of electrons between different energy levels. So this principle also I have explained in the previous lecture in terms of what is the emission, what is absorption. So I think this is just a repetition of it. So basically, we can look at in terms of emission, is that your sample which is in the excited state produces light or loses energy going back down to ground state. While in terms of absorption, the sample takes up energy which consumes the light of appropriate wavelength in terms of for it to become excited from a ground level to an excited level. Okay. So, atomic spectroscopies, now we need to focus on atomic spectroscopy. So, atomic spectroscopy is a technique for determining the elemental composition of an analyte by its electromagnetic or mass spectrum. So, now we are going to look at the elemental level. UV-vis, molecular level, but for atomic spectroscopy, you're going to look at elemental level. Means that, for example, now in terms of UV-vis, your sample might be paracetamol, catechin, chlorophyll, but for atomic spectroscopy, you are going to look at ferrum, you're going to look at iron, you're going to look at plumbum, you're going to look at mercury, okay? So all of these elements, so that's why when we are going back down to atom level, so your molecules needs to be atomized first before we do any atomic spectroscopy. Okay, so atomic spectroscopy are divided into two, which is optical spectroscopy and mass spectrometries. So basically for optical spectroscopy, we are going to look at AES, which is atomic emission spectroscopy, AAS, atomic absorption spectroscopy, and then fluorescence spectroscopy also we do have, and then the third one which is the one that we are going to learn as well, which is the ICP-MS, which is inductively coupled plasma mass spectrometry. It doesn't matter with all of this word jargon, you will look at into in detail later on. All right. So atomic spectroscopy. So these are the techniques in terms of what is there going to be used in terms of atomization, in terms of how for it to become excited, and then what are kind of the samples. So maybe if we look at AAS here, so the samples usually is in the liquid sample, right, which is sprayed into the flame of furnace. So now you can imagine that, okay, because before this I have explained that all of these instruments have a schematic diagram, so you should be able to imagine that, okay, by this table you can look, in AAS there must be a flame and there must be a furnace, something like that, okay, to get an idea of it. So for this table, you might read it. Okay, methods which is based on atomic spectroscopy. Okay, as we have looked before, atomic absorption spectroscopy, AAS, it measures the absorption of radiation by atoms in the gaseous state. So now, as it names, you can know that by atomic absorption spectroscopy, it measures absorption. So whatever that has been transmitted, you can get the absorbance. Okay. For atomic emission spectroscopy, it measures the emission of radiation from an excited atoms, which when it becomes excited, then when it relaxes, when it undergo relaxation, it can also emit electromagnetic wave, which is called emission. Okay, so this atomic emission spectroscopy might come from flame emission spectroscopy, inductively coupled plasma spectrometry, and also atomic fluorescence spectrometry. So all of these instruments rely on the emission part. Yes, it has been absorbed, but it doesn't measure the absorption, it measures the emission. So you need to really differentiate between absorption and emission. During UV visible, you just focusing on the absorption. So whatever the transmittance, you divide it, you get your absorbance. But for emission, you need to really understand the difference between these two, because emission also releases wavelength, electromagnetic wavelength. Absorption also has been releases transmittance. Okay. All right. So this is might be a figure that you might be able to understand much more better. So the common principles is that for atomic spectroscopy, you need to imagine that before we go into each of the instrumental part, you need to know that we need to have some kind of sample introduction, which is nebulization and evaporation. Okay, so atomization, as I mentioned, it needs to be atomized first before it has been analyzed. So atomization and excitation by flame, furnace, or plasma. So spectrometer components as the same as UV visible, you need to have a light source, okay? And then we need to have some kind of optical system, okay? And then a detector. So at this picture, you can also look at the difference between what kind of atomic absorption and atomic emission and also atomic mass spectrometry. Okay. The instrument components. So this also is a part of a schematic diagram. Okay. So basically, the difference between AAS, ICP-OAS, and UVV spectrometer, you can look at it. Means that AAS, we have a light source, and then the light source would go into the sample, and then the sample would create some kind of absorption, and the transmittance are going to be uh, created by the monochromator and the detector. We are going to look at in a very detail after this. Okay, so you notice that the difference between AAS and UVVs, the monochromator is at a different position. AAS, the monochromator, it is at after the sample, while the UVVs, the monochromator, it is before the sample. All right, so there's a function why the monochromator is after the sample or why the monochromator is before the sample. So UVVs here, before this, we look at the monochromator is before the sample because the monochromator, the function of the monochromator is for you to be able to only select a particular wavelength for your sample. But why for AAS? It is after the sample. We will be looking at after this. All right. So this is an example of atomic absorption spectroscopy instrument. So I think that you will be looking at this maybe in your lab session. I'm not sure. All right, so this is a periodic table where all of the metals in the transition period, also between the first, second, uh, also can be detected by AAS because it is an elemental spectroscopy. All right. So basically, this is the AS flame spectrophotometer. You can just take a look at it. This is the view of the inside of the instrument. On where is the monochromator, where is the photomultiplier tube, okay, where it's the source. So the source is hollow cathode lamp. This is the burner, the nebulizer, the atomizer also is here. Okay, so now we are going to look at into the detail of a flame atomic absorption spectroscopy, flame AAS. Okay, so why we put it flame? There is a reason. Okay, so flame atomic absorption spectroscopy is the simplest atomization. The level of detection is at a ppm level. ppm, microgram per liter. Okay, it is relatively insensitive, incomplete volatilization. Less than 5% of the solution is converted into atoms in a short time in the flame. It is reproducible, it is very low cost per analysis, and it is rapid. Okay, so basically, this is the maybe you can call it advantages and also disadvantages of flame atomic absorption spectroscopy. So now you can look at we have a source here. We have a source of your source of light, and then we have a chopper here. There is a function of this chopper, okay, and then your sample will be going into the nebulizer and also being atomized inside the flame. So this is flame. So flame here represents the atomizer, and then whatever the wavelength, in this case, the transmittance from the absorption during atomization in the flame will be detected by the wavelength selector. So the wavelength selector here is the monochromator, and then the particular wavelength your uh, from your transmittant will be detected by a detector and will processed by a signal processor readout. Okay, now we are going to look at the light source, which is a hollow cathode lamp. Okay. Why does it call hollow cathode lamp? Okay, the source of a light is a lamp whose cathode is composed of the element being measured. Okay, here the light sources for your AAS, flame atomization spectroscopy, flame atomic absorption, sorry, spectroscopy. This source is a line source. Okay, what a line source means that this light source would just produce one kind of wavelength. Means that if you are detecting arsenic, so the light source must be an arsenic hollow cathode lamp. Kalau you nak detect copper, it must be a copper hollow cathode lamp because the element that you are going to being analyzed is at the cathode of the lamp. So means that it just produce one kind of one kind of wavelength for the excitation of your particular analyte. Faham tak? In UVVs, the light sources produce a range of wavelength. So it needs to be filtered out by your filter, and if not, being filtered out by your monochromator. But for AAS, atomic absorption, we just use a light source which is very particular, very specific towards your analyte of interest. Okay. Each analyzed element requires a different lamp. So this is what I said. So when you are, for example, you are trying to detect arsenic in a water sample. So you need to change the holocathode lamp to an arsenic holocathode lamp. The lamps are stored in a compartment inside the AA spectrometer. The specific lamp needed for a given metal analysis is rotated into position for specific experiment. So basically now, for this picture, you can look at, we have 4 types of lamp here, which corresponds to a different element. Okay. So the process that occur inside the holocathode lamp, what is the process in the holocathode lamp? Okay. Inside the holocathode lamp, you bayangkan dalam mentol lah. Okay, dalam mentol. Okay, so inside the mentol, inside the lamp, there is an argon gas, an inert gas. Okay, so this argon gas, okay, let me go step by step here. So the first step, you are going to do copper analysis. Okay, a hollow cathode lamp, a hollow copper cathode lamp is needed. So that's why I say kalau you ada arsenic, you nak try analyze arsenic, then you need to have a hollow arsenic cathode lamp. But in this case, we are using copper. Okay, step 2, sputtering. So the argon gas inside the lamp is ionized by electric current. So the first step is argon gas is being ionized. And these ions are attracted to the cathode. So argon gas punya ions, which is Ar plus, it will be attracted to the cathode, where at the cathode is the element for your particular analysis. In this case, there is a copper element at the cathode. So what does this argon ions do to the metal? In this case, copper. The inert gas ions bombard the cathode, and in so doing excite the metal ions coated on it. So these argon gas ions bombard the cathode, where the cathode you have a copper metal, where this bombardment of argon ions towards your metal would excite your metal. It will excite your metal. So this excitation of the metal produces the emission of radiation with wavelength characteristic of the analyte. So when your metal have become excited, remember when this bombardment would create your element from ground level, it become excited to an excited level, but the excited level is not stable. When it is not stable, it needs to go back down to the ground level. So from the excited level to the ground level, it releases an emission of electromagnetic radiation at that particular wavelength of copper. So that's why when you want to analyze copper, you use copper holocathode lamp, because only copper holocathode lamp can produce a wavelength which is very specific towards copper in your sample. Okay, up until this point, I do hope that you understand. Okay, all right. So, holocathode lamp is made of a tungsten anode and a cathode made of an analyzed element sealed in the glass tube filled with neon or argon. It doesn't matter. It is an inert gas. The analysis of a particular element must make use of a unique lamp for each of the elements. So you would imagine that from your lamp, it produces a wavelength particular to copper. Okay? And then those particular wavelength would go into the flame, where your sample has been nebulized and atomized. So only copper ion or only copper metal inside your sample would be excited by this wavelength from the lamp. All of other elements will not be excited, because the wavelength is very particular towards copper. Okay, so now you imagine yourself in the lamp with the copper. So now you have a light from the hollow cathode lamp. So it excited your copper metal inside your sample. So your sample will become excited. The copper will become excited, means that it is absorbed, and then you produce a transmittance. So those transmittance would be used as a readout later on. Okay, I do hope that you can imagine it. Okay, because if it is face to face, I can show you much more better in terms of the process of EAS, or even so any kind of instruments. All right, moving on. So the hollow cathode lamp for let's see in terms of this example, the hollow cathode lamp for plumbum concentrates emitted radiation specifically for plumbum into a beam which passes through the window to the vaporized plumbum sample so that the same radiation can be absorbed by the plumbum atoms in the sample. So this is what I have explained just now. So you imagine yourself, you imagine the copper atoms being excited by the copper wavelength inside the lamp. Okay. This is the second one, which is electrodeless discharge lamp, EDL. So EDL is made of a metal or salt of interest sealed in a quartz tube filled with neon and argon at low pressure. It is energized by a field of radio frequency or microwave radiation for the ionization of argon to give a high frequency accelerated component. So basically, the function is quite the same, but EDL have much more advantages as compared to hollow cathode lamp. And the advantages of EDL is that it is able to use the light generating substances that would react with metal electrolysis in a normal lamp. And it also have extended bulb life. Okay, usually I think that for hollow cathode lamp, after a few, not a few lah, maybe about uh, 20 to 30 times of analysis, you need to change the light, the hollow cathode lamp, sorry. Okay, but for EDL, it has much more extended bulb life lah. The electrolytes are usually limiting factor in the bulb life. So EDL is much more intense and sensitive as compared to hollow cathode lamp. Hence, it is better precision and has a lower detection limit. Okay, EDL are available for a wide variety of elements. Okay, sometimes you will not have ECL, collocated lamp for all of the elements, but maybe electrolysis EDL, we do have the particular element. All right, so that is the light source, the first part of your schematic diagram. The second part is the sample introduction. The sample introduction of how are you going to introduce your sample now. So where to put your sample? Kalau in UV vis, you put your sample inside the cuvette. Kan? You put your sample inside the cuvette, so you do your analysis whether it's by single beam ke double beam ke, doesn't matter, but the sample you put inside the cuvette. But for atomic absorption spectroscopy, how are you going to do it? Okay. So for sample introduction, the samples are dissolved in water. So now you can know that straight away. For AAS, you need your sample to be in a liquid form. The sample are dissolved in water, and then the film is created usually using ethane, and oxygen fuel. The aspirator here, okay, if you can see that there is an aspirator here. So this is your sample diluted in water. So your aspirator here would suck the liquid into a small tube from the sample container. After your sample has been sucked into the instrument by the aspirator, fine aerosol is created. You bayangkan you would imagine that your liquid and then flows into the into the burner, then it will straight away evaporated. Means that it will create a fine aerosol first. Maksudnya it moving towards become evaporated. Okay. So fine aerosol is created and was mixed with fuel and oxidant for the introduction into the flame. The liquid is transferred to the flame where the sample undergoes atomization. So this is very important for this process. After liquid become fine aerosol become atom. But before fine aerosol become atom, there's a lot of other process lah, because atom tu is the last part. Okay, so usually liquid to vapor, which is in this case a fine aerosol, liquid into fine aerosol, and then fine aerosol into molecule into atom. Okay. Kita ada molecule. The first stage is molecule. The liquid is transferred to the flame where the sample undergoes atomization. The metal atoms then would absorb the light from the source. Okay. So the overview, now you can look at the longitudinal view. All right. So this is the burner head. So this is the burner head. You imagine that your sample are here, sample here. So it will be sucked into the sample capillary into the nebulizer. So it becomes an aerosol here and mixed with oxygen and fuel and then flow into the burner head. So it will become atomized here at the burner head. Okay. So the burner head, So you will imagine that from this left to goes to the right. So so the flame is going to be this long. It depends on the burner head. Okay, the burner heads are constructed of titanium to provide extreme resistance to heat and corrosion. So we have a 10 centimeter single slot burner, which is recommended for air acetylene flames. It produces a small blue flame lah. So small blue flame means that we are trying to achieve a complete combustion. It as a long length provides the best sensitivity. We also have a 5 cm burner head, which is recommended for nitrous oxide and acetylene flame. Okay, so this is the example of the burner head that we do have. So you will remember that you imagine that all of your analytes will be atomized at this burner head lah, at the burner head level. Okay. All right, so this is the oxidant fuel. I think that you can read this on your own in terms of the combination of air, acetylene, nitrous oxide, acetylene. Okay. All right. So atomization process. Okay. Atomization process, which all of these are going to happen inside your sample introduction part lah, from the aspirator towards the atomization at the burner head. Okay, so atomization is the process of converting sample, which is solid or solution, into vapor particles, individual molecules, and then individual gaseous atom using an atomizer. So, the process, you will look at the converting the solution to aerosol form, which we call it nebulizing or aspirating. And then after it forms aerosol, we remove the solvent, which is called desolvation. So Ma solution, it becomes Ma solid because you have take away the solvent, which in this case water. And then vaporization, from solid it becomes gas, and then atomization, it will become M, which is your M gas and A gas, okay, into individual gaseous atom. So after it had become a gaseous state, the fifth step is that the excitation step, from the ground state to an excited state. The excited represented by this asterisk. And then it is not stable, as I mentioned before, then it will create an emission. So this emission, M star, become M ground state. So this is very particular to your AES, not AAS. So AAS is up until excitation only. Okay, so for emission, it will if it is continued to emission, then it is for AES, atomic emission spectroscopy. But for atomic absorption spectroscopy, it is just until your excitation state, because we would measure the transmitters, not the wavelength that is being produced by the emission. And then the seventh step, which is ionization, which is undesired for our part of analysis. It doesn't matter whether this is an absorption ke emission ke, but ionization we don't want. Okay. But it will sometimes it will happen inside your atomization process. Okay. Let me check first. Okay, so this is an atomizer. Okay, now we are going. Tadi kan we look at into flame atomizer. So now we are going to look at there is another types of atomizer which is a graphite furnace or electrothermal atomization. So this is flameless. There is no flame here. There is no flame involved here. But the flame is replaced by an electrically heated graphite tube and heated electrically. Okay. So you imagine that okay, so in this case macam mana our sample needs to be aspirated, whatever, aspirated lah, dissolvation lah, whatever. So when you are using graphite furnace, it does not it doesn't need to be aspirated, it doesn't need to be apa uh, it doesn't need to be in liquid form. It can also be in a solid form because a few microliter sample is placed in the tube, dried, ash, and then vaporized at the high temperature. So you can just put you imagine that the graphite furnace is something that is you imagine that there is a plate there. You just put your sample in. It doesn't matter whether it's liquid or solid. You just put your sample, and then when it is heated, all of the processes are going to be uh, are going to follow through lah, which is the dissolvation, gaseous, turning from vaporization from solid to gaseous, excitation, emission. So everything will happen at the same time. Okay. The atomization efficiency is greater than for a flame. Okay, the temperature program can ensure reproducible atomization. Sample is atomized at a very short time, while in for flame AS you would require some time because you have a lot of processes beforehand. You need to be aspirated. So before it can be become atomized, you have dissolvation, evaporation, whatever. So for graphite furnace, you just put your sample in, and then it is doing all of the processes at the same time. Excellent sensitivity, low detection limit up to PPT part per trillion, and less reproducible. Okay, so this is graphite furnace. So you need to be able to differentiate between flame AAS and graphite furnace AAS. Okay. So this is just the instrument part of it. I think that you can watch this video later on during your own time. Okay, so this is a schematic diagram of a graphite furnace AES. So basically, I would say that it's quite the same in terms of we do have a light source. This is the graphite furnace. You put your sample in, so all of the atomization, excitation, emission would happen in this graphite furnace, and it will be the wavelength or the transmittance will be converted to monochromator, and it will be detected. So this is the graphite furnace lah. When you look at, you just put your sample in, and then you put your sample in, and then the optical path here is where your light source comes in. So if it is a copper, so a light copper source, something like that. Okay. So the flame is replaced by an electrically heated graphite tube. So a few microliters of sample is placed onto the tube. It is dried and ashed at lower heats and then vaporized at a higher temperature. The atomization efficiency is greater for a flame and the detection limit is lower. Okay, why does the determination of arsenic is sensitive using GF graphite furnace but not flame AAS? Okay, so this question, as usual, I want you to answer it. You need to find it and then jot down on a piece of paper and then answer it and put it inside the e-learning after you have done. Okay, so this question will count as your attendance, okay? All right. So these are the graphite furnace program, which is what? Drying, pyrolysis, which is we call char, and then atomization. Okay, so drying, it will be carried out, for example, for drying purposes, it will be carried out at the 10 to 100 second, and then the temperature will rise from 50 to 200 Celsius to remove the solvent. And we continue with char, where we decompose the matrix, which the temperature goes up to 800, and then atomization, which is the temperature would go up to 3000 Celsius. Okay. So this is the comparison from flame and graphite furnace. So you need to be able to, I know, to get the gist of this, okay, because this is a popular question to ask in terms of what is the difference between flame AAS, what kind of sample that can be used for flame AAS ataupun for graphite furnace AAS, which is more suitable, which do you think can get much more better results? Okay, so I think that you can just read this. I think this is very straightforward, okay, as what I have explained before. So these are the detection limit lah for your apa, for your element of interest. So to increase the sensitivity of atomic absorption, the easily ionized elements such as K plus could be added to prevent targeted analyte from being ionized. Okay. So usually this is the tips in terms of how would you increase the sensitivity of flame AAS, not just flame lah, because usually when it goes an atomization process, it will lead to the ionization part, which is the number 7, that the one that we not desire. But for that, we want to minimize for our analyte to become an ion. Usually we would add elements such as K plus lah for it to become ionized first. Okay, so the application of atomic absorption spectroscopy in terms of graphite furnace, so you will be able to analyze mercury analysis in seafoods. You'll be able to determine trace elements or analyze of heavy metals, or even in forensic science as well. You can use application AAS graphite furnace. So I think that I can. Okay, so the determination of arsenic in cockles. Okay, so this is one of the example, one of the application for AAS. So you would know that cockles, or in this case we call kerang lah. Okay, so kerang ni dia kerang ke kupang ke, it is called as the filters for our laut, okay, for our seas. So when it acts as a filter, so for some time, it can also absorb heavy metals, which is being released uh, by people who are not responsible lah. Okay, so we want to detect whether the arsenic can be absorbed by the cockles. So the arsenic is present in several forms, which can lead to different toxicities lah. So so how are we going to do it? So in terms of sample preparation, you will just collect the cockles, isi kerang itself, the cockles flesh, and then you would do a microwave digestion, which we will learn after this in terms of digesting for, I mean, the sample preparation for inorganic analytes. Okay, and then after we have done the digestion, we can just straight away do the analysis. All right. So yes, so now so this is a part of the sample preparation. You will learn this much more, I think, in chapter, so after this ICP chapter 5 or chapter 6, something like that. Okay. All right. So okay, analysis of sample. So you need to prepare a calibration curve. So calibration curve is something that you will use for quantification purposes. So I think this also you will learn later on. But it's good for you to have some kind of introduction to it of how the process would work. Okay, so I think this process is important for you to know, just to know, but you will be explained later throughout the semester in terms of how to do this calibration curve, on how to evaluate, how to determine on how the results which is shown here. So this is a calibration curve. So this is the results that they have got, and then what is the meaning of these results. Okay. All right. So the conclusion is that below 1 kilo of arsenic in cockles will lead to exceed of PTWI threshold for 0.015 milligram per kilo per week. Okay, so there is a threshold here. According to the Malaysia food regulations, maximum permitted proportion of arsenic is 50 microgram per liter. So in this experiment, all of the sample are safe to consume as they have lowered, uh, they have much more lower content of arsenic inside the cockle shell. So this is determination of arsenic in wastewater. So you can have a read also, and this is very important, okay? You can have a read also in terms of the process. It also have a digestion as well. Okay. All right, I think that we can stop at this slide before I go on to the hydride generation. Let me see. Okay, I think we will stop here first. All right, thank you guys.